In this example, we are going to determine the electric flux through a hemispherical bowl of radius 2 meters due to a -6 microcoulomb point charge at the center of the bowl. A hemispherical bowl is just half of a sphere. To answer this question, we are going to employ Gauss's law. Gauss's law is a profound idea from physics, and it tells us that the total flux through a closed surface is equal to the total charge inside that closed surface divided by an appropriate constant of nature. So how do we use Gauss's law here? Notice that Gauss's law says our surface must be closed. A closed surface could be thought of as a boundary that separates a region of space we call inside from a region of space that we call outside. And it's impossible to move from the inside to the outside or vice versa without passing through the boundary. To address this question, let's not consider the bowl with the point charge at the center. Let's first consider a different problem. Let's take a -6 microcoulomb point charge, just like we have up here, but I'm going to instead place this negative point charge at the center of a sphere of radius 2 meters. So here is my sphere of radius 2 meters. And this sphere is a closed surface. There is a notion of inside the sphere versus outside. So I can use Gauss's law to determine the total flux through the sphere. If I do that, I would say the total electric flux through the sphere is going to be equal to the total charge inside the sphere. We said this point charge is -6 microcoulomb, just like here. So I would have -6 times 10 to the -6 times 10 to the -6 because microcoulomb, and divided by a fundamental constant nature. I go to the back of the book, look up epsilon naught, and it is 8.85 times 10 to the -12. When I put these numbers in a calculator, I find that the total flux through the entire sphere is going to be -6.8 times 10 to the 5. And the units of flux are Newton meters squared per coulomb. Let's look at the two pictures we have. Here we have a sphere with a point charge at the very center, and here we have a bowl with a point charge at the center of the rim of the bowl. Looking at these two pictures, I could recognize that the bowl is exactly identical to the southern hemisphere of the sphere. Because the point charge is located at the center of the sphere, I could reason that half of the electric flux that passes through the sphere will pass through the northern hemisphere, and half of the electric flux that passes through the sphere will pass through the southern hemisphere. Therefore, because the bowl is identical to the southern hemisphere, I could say the total amount of electric flux that passes through the bowl will be equal to half of the total electric flux that passes through the sphere. So I could say the total electric flux that passes through the bowl is going to be 1/2 of -6.8 times 10 to the 5. And so I will get the total electric flux through the bowl is going to be -3.4 times 10 to the 5 Newton meters squared per coulomb. There are two comments I would like to make about this problem. First of all, we are able to solve this problem because the electric charge is at the very center of the bowl. The first comment I would like to make is we said the point charge can be found at the center of the rim of the bowl. This was a very important detail that made the problem solvable. Let's think about what this problem would look like if we were not provided this detail. So let's say here is a side view of the bowl, and instead of placing the point charge at the center of the rim of the bowl, we'll place the point charge near the bottom of the bowl. When we solved this problem, we had to convert this bowl from an open surface into a closed surface. So what we did was we gave the bowl a northern hemisphere, we converted the bowl into a full sphere, however you want to think about it. So I will go ahead and do that. And then we applied Gauss's law. Because we have the same total charge inside our closed surface, we will have the same total electric flux through that surface. But remember, the amount of flux through a given patch of area on the surface will depend on the strength of the electric field at the location of the patch of that surface you're looking at. And the strength of the electric field will depend on the distance from the point charge. If I'm very close to the point charge, the electric field is going to be very strong. But as I move further and further away from the point charge, the electric field will get weaker and weaker. A consequence of this is that because we moved the point charge closer to the South Pole, locations in the southern hemisphere are going to have a stronger electric field, and locations in the northern hemisphere are going to have a weaker electric field. That will imply that the total electric flux through the southern hemisphere will be greater than the total electric flux through the northern hemisphere, because the electric field in the southern hemisphere is now stronger. The total electric flux through the entire sphere is still going to be the same. It's still going to be negative 6.8 times 10 to the 5, because we still have the total charge inside the sphere, but it's no longer evenly distributed. So we could no longer just divide the total flux by 2 to get the flux through the southern hemisphere. It'll be some other distribution. The second comment I want to make is notice that we never used the radius of the bowl in this problem. Gauss's law does not care about the size or shape of the surface that you're considering. Gauss's law only requires that you work with a closed Gaussian surface. And in some special cases, when we have a high degree of symmetry in a problem, we could even get around the requirement of a closed surface. The power of Gauss's law could be demonstrated by considering a point charge surrounded by a spherical Gaussian surface. So we're going to consider a setup similar to this. Now, first of all, I want to say, normally we would not want to draw the equator in, but I chose to draw the equator in this picture to provide a notion of perspective, since this is a 3D problem. Notice that this setup has a very high degree of symmetry to it. If I change my vantage point, I will still see the exact same image as long as I am the same distance away from the point charge at the center. There will be some amount of electric flux passing through this surface, and if I want, I could imagine the surface as being divided up into many small patches, and each patch individually will contribute an amount of flux EA cosine theta to the total electric flux through the entire sphere as a whole. So for example, I could imagine that at the location of patch number 1, there will be electric field E1 passing through that patch. And the total electric flux through patch number 1 will be the strength of the electric field E1 times the surface area of patch 1, which is A1, times the cosine of angle theta 1, where theta 1 is the angle between the direction of electric field E1 and a line that is perpendicular to the surface at the location of patch 1. Similarly, patch 2 will contribute flux phi 2, which is the strength of electric field at the location of patch 2 times the surface area of patch 2 times the cosine of the angle between the direction of electric field E2 and a line that's perpendicular to the surface at the location of patch 2. And similarly for patch 3, patch 4, and so on. Notice that due to our choice of a sphere surrounding a point charge, the electric field will have the same magnitude everywhere on the surface of the sphere. So the magnitude of electric field E1, E2, E3 is going to be the same everywhere on the surface of the sphere. Also notice that the direction of the electric field is always going to be perpendicular to the surface of the sphere, no matter where you're standing on the sphere. So that is essentially saying that these angles, theta 1, theta 2, theta 3, are all going to be 0 degrees everywhere on the surface of the sphere. This will greatly simplify the problem that we are considering. So I could replace E1, E2, E3 with the same E because it is the same value of electric field everywhere. I could replace all of these angles with 0. So if I think originally of the total electric flux as the sum of electric flux through patch 1 plus the sum of electric flux through patch 2 and so on, as we wrote on the previous slide, then I notice that the cosine of 0 is just equal to the number 1. And I could write, therefore, the total electric flux over all of the patches that make up the entire sphere could be written as E times A1 plus A2 plus A3 on and on. And so the total electric flux over this entire sphere is just going to be equal to the strength of the electric field at the surface of the sphere times the total surface area of the sphere. Now, when I write this equation for the electric flux in Gauss's law, I could set E times A total equal to Q enclosed over epsilon naught. And I look up the surface area for a sphere of radius r. And I could replace A total with 4 pi r squared. By rearranging this equation, I could find an equation for the strength of the electric field at the surface of the sphere. And that is E is equal to 1 over 4 pi epsilon naught times Q over r squared. So notice that we made no assumption about what the equation for the electric field is. We only said that the electric field should be the same at the same distance everywhere away from a charge. And we were able to derive the equation for the strength of the electric field a certain distance away from a point charge.